we have discussed in our first lecture that certain secondary operations are needed after the sintering process. Even after the sintering process, some of them are just like number one is the repressing. So in the repressing operation is that operation in which the part is squeezed in a closed die to increase the density and improve physical property. So once the part is sintered, sometimes it has some dimensional inaccuracy, sometimes it has some density problem, and some porosity is also there. So what you do that you again repress the part in a closed die, and then you apply a certain pressure, compaction pressure, in order to increase the density and to improve the physical properties. Then sizing is a simply repressing and sizing, both can be done simultaneously. The sizing is pressing of a sintered part to improve the dimensional accuracy, and it is done after the sintering operation. Sometimes in sintering operation, what you see, you observe the dimensional distortion occurring due to the rapid change in the temperature. If you have not controlled the furnace temperature, if you have not controlled the temperature in the cooling zone, then it may lead to the setting up of the residual stresses, which will deform your part, and that part cannot be used for the actual working application. Therefore, the sizing is required, and this sizing is basically referred to the pressing of that sintered part which has lost its dimensional stability and dimensional accuracy. So it will improve its dimensional accuracy by repressing. And sometimes some part needs some impressing and some embossing on the surface. So we require one process which is called a coining process. So coining is a press working operation on the sintered part to impart or to press some details on it. So it may be some manufacturer mark, it may be some part number, or anything which you want to highlight on the surface of your sintered product. Then this coining is used. Then after this, there is a process which is called machining. You all know that if somehow some extra material has left onto the surface, and if you want to produce some holes into the sintered part, and if you need some threading on the sintered part or the finished product, sometimes rarely this machining is required, because we have already studied that this powder metallurgy operation is a near net shaped manufacturing process. So machining is rarely done, but sometimes you require some internal and external features like thread, like side hole, maybe some cuts, some undercuts. So machining is rarely done to impart such features on the surface. Then after this, we have a very important process which is called impregnation. So in the first slide, I had mentioned about this impregnation technique, that this is basically used to make the oil impregnated bearings. And basically impregnation is the term used when some oil or some other fluid is permeated into the pores of a sintered powder metallurgy part. So you all know that even after the sintering, some voids they can be left inside the material, and those voids and pores can suppose in case of this bearings, these oil impregnated bearings, you require some automatic lubrication, so that in during the working condition, if you apply some pressure or the shaft is rotated very high speed, and some vertical loading is applied on the shaft, so at that time it will cause more friction in the bearing. So at that time, if you use this oil impregnated bearing, it will give automatic lubrication, because the lubricant is clogged, or basically it is holded inside the pores in these tiny holes, and it will come out automatically when the shaft or when this bushing is under the actual working condition. So that it can retain 10 to 13% oil by its volume. So this is the impregnation process. And then you have the infiltration process. So infiltration is an operation in which the pores of powder metallurgy part are filled with the molten filler metal. So not always this porosity is desirable. In most of the engineering applications, this porosity is a problem, or it's basically a basic reason behind the failure of the part. So even after the sintering process, some voids or porosity is left inside the part. In order to fill those porosity, we take our part, we dip this powder metallurgy sintered part into a bath of the molten filler metal, and this molten the melting of this melting point of this filler metal must be below that of the powder metallurgy part. For example, the copper infiltration of iron powder metallurgy part. So you can see from this high magnification scanning electron microscope that this you can say the golden or this light brown color is of this copper material, which has infiltrated into the pores present in this in powder metallurgy sintered part. So this infiltration, in some books you will find the reverse of it. Infiltration means the filling of the oil and other fluid, and impregnation means the filling of the molten filler metal. But I have taken this from a very good reference with some authentic reference. So the exact definition of impregnation is that filling of the pore with the help of the oil, lubricant, or some organic fluid, and the infiltration means the filling of the pore with the help of a lower melting point filler metal. So there should not be a confusion. Many times, in most of the times, when I ask this question, the student, they read some books which have mentioned the reverse of it, and they do it wrong. So I request you to stick to this point, that infiltration means the filtration, the infiltration of your low melting filler metal into the pores and cavities of a sintered part. And impregnation means the impregnation of the oil and other organic fluid into the pore cavity. So this is our last topic, which is called the design consideration in the powder metallurgy parts. The Metal Powder Industry Federation, which is MPIF. This is basically the organization which sets the standards for this powder metallurgy technique, or the parts which are going to be used in some practical application. So this organization take cares of all the standards, and it is a regulatory body. If you have, suppose, if you are going to set up your powder metallurgy industry, then you must have some recognition from this Powder Metallurgy Industry Federation. This is a global organization which gives you recognition, and it gives you some quality standards, some quality inspection certificates, so that you can show it to your clients and you will have a great name in the market. So this Metal Powder Industry Federation, it has defined 4 classes of powder metallurgy part design. Okay, depending upon the level of difficulty in conventional pressing. So have basically 4 types of powder metallurgy part design. So the first one, figure A shows the class 1. So this is the class which has simple thin shapes that can be pressed from one side. So you see that this is a very thin shape, and very simple part, so that it can be pressed from one direction, and then you can get the required density and the required properties and performance. Okay, and then class 2 is simple, the shape is simple but thicker shapes, and it requires pressing from 2 directions. So this figure B, you see that here it has almost twice or thrice 3 times the thickness. So in this case you would require pressing from both the direction, from the top side and from the bottom side. So here it will involve 2 type of punches, from one working from the top side and other working from the bottom side. Then C is basically your class 3. So it has 2 level of the thickness. You see that this is one level, and this is your second level. So here you have a stepped part. So that means the pressing will be from this direction also, and from here also, and from the top side also. So here you have basically three types. You have two level of thickness, and the pressing is required from two sides, from two direction, from top side from and also from the bottom side. And finally we have a class 4. This is more complex design, and it can have multiple level of thickness, multiple steps in your part, and pressing required from both the direction, from the top side of both the sides, and it requires separate control for each level to achieve proper densification throughout the compact. So these are basically four broad categories of powder metallurgy part design, and it depends upon the level of difficulty in conventional pressing. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.